verify if, not verify that.
Alright, verify that this is true. Well, how can I verify that this is true? How can I verify that the antiderivative of u sine u is this? Differentiating, right? Just differentiate sine x minus x cosine x, and hopefully we just get x sine x. Well, do we? I think so. Derivative of sine is cosine, and the derivative, so this is now minus the derivative of x cosine x, which is the derivative of the first times the second, plus the first times the derivative of the second, which is negative sine. And when you multiply that out, you just get cosine minus cosine, and then minus negative, so you just get x sine x. Okay, so their formula has been verified. So essentially, they just taught me a fancy derivative by just a fancy antiderivative by just telling me that, and then asking me to double check. And now, somehow use this fancy antiderivative to integrate from 0 to pi squared of sine root x dx. Show that that is 2 pi. So show this. So they're also giving you the answer again, so you can kind of double check that you're doing it right. Well, I don't know how to anti-differentiate sine root x. So let's try some kind of substitution. I think I should just let u be root x. Well, if I let u be root x, let's see, then du is 1 over 2 root x dx. And that seems problematic because I don't have that there. So I have to kind of put it in and like put it back, right? I'm going to basically multiply the top and bottom by 2 root x over 2 root x. And if I do that, then this suddenly becomes, well, it becomes sine of u, and then like this part is the dx, right? Can I get like a green or like a red, blue? Green's nice. Yeah, you just throw it. Yeah. So this is just du, right? So this is sine u du 2 root x, and this is going to be u of 0 and u of pi squared. Well, I think you just see this whole thing working out, right? Because root x is just u. So actually this just becomes 2 integral from 0 to pi of, no, not squared anymore because I rooted it, of sine u, of u, basically u sine u du, which I did not previously know how to do, but now by part A, I know the answer is just sine u minus u cosine u. And I will evaluate that. Oh, and there's a 2 also out here. And I'll evaluate that at 0 and pi. So this is 2 times sine of pi, which is 0, minus cosine pi is negative 1. A lot of negatives going on here. Cosine pi is negative 1, so that's negative pi times negative 1.
Minus 0 times 0.
Minus, and when I plug in a 0, I get 0 minus 0. So that's negative pi times negative 1 is pi. So final answer, 2 pi. Are we good? Yes.
I don't really understand how we got from like negative thingy from 0 to 1, from 1 to 0, all that to the other
This step to this step?
Yeah.
I just flipped the negative. This is the integral from that flips it.
And then reintroduce u as y plus x.
No, I don't even think you have to. It's just done.
But that's not what we were trying to prove there.
Oh, we were. That's exactly. These two are exactly the same. Just the variable's different. That's all. It's a dummy variable.
Remember, variables don't matter.
Oh.
All right. Can I have this homework? Should I just collect the homework later to be nice to you guys for coming, or do you want to collect it now?
Oh,
You're gonna have bonus
yeah,
points.
just all the
No, bonus points.
Yeah.
Anyone give me like 13 out of 10. Anyone who like that.
That's for the rest of it, though. Think about the whole.
Think method what?
That's faster.
Explain what?
The, like, I don't know, the expectation of having I get stuff done.
What? Yeah, this homework, as I just said. Yeah, this is gonna be like 15 out of 10. All right, is that, do I have all the homework basically? Boom, boom.
Oh, yeah.
All right.
Did you hit
15
pause?
minutes. Should we just start our cool thing? Let's
Should we
start our cool
pause?
thing. No, don't pause, just keep it running.
Why would we pause it?
Yeah, why would we pause it? All right, so we're gonna do something that's pretty cool. And this is what we're gonna basically talk about starting now is error. And we're gonna continue talking about error. It's starting this class and it's gonna go for an entire another block. So this is one of these subjects that's just so big that it's gonna basically take 2 classes.
Whoa.
And this is also kind of fun, a little bit for me, because this is something which they normally taught in Analysis 1B, but Stein wanted it to be in Analysis 1A, and I just fought him for years about that because it just seemed really hard and it was going to take forever. But, so this year I'm doing it for the 2nd time, but last year was terrible. So I spent endless hours preparing this really cool, fun lecture, and I took a really difficult subject. Hopefully I made it really clear. So I have high standards for this working out really, really well, so I hope it does. So that's the setup for like maybe. All right, well, Aaron, are you ready? Open your mind to like new thoughts and concepts. Good. So what I want to talk about basically for the rest of the period is this thing called numerical integration. What is numerical? So what is numerical integration? It is basically integration by not using the FTC. Integration by kind of just cranking it out with a calculator, or possibly by hand. And here's the problem. This might have been I think period 8 might have been the one class where I did previously mention this fact. The FTC is really, really great for computing integrals. But it only works when it works. And when it doesn't work, it doesn't work. And there's a bunch of times when it doesn't work. For example, and so this is kind of sad actually. So now the glory of FTC Day, now that it's passed for a couple days, I want to remind you that sometimes it will simply just not help you. For example, the integral from 0 to 1 of sine of x squared dx. Well, you might think, hey, I know the FTC. Let me just come up with an antiderivative of that, and then I'm just done. Guess what? There just isn't any. This is a sort of a weird idea, but there just simply are no antiderivative. This function does not have an antiderivative. You can try all kinds of obscure substitution patterns. None of them, and it's just not going to work. Okay, here's some more. The integral, so even seemingly simple functions possess no antiderivative. Again, that looks like a problem that you should be able to solve probably, but it just isn't. And even I'm very experienced with solving anti-differentiation problems. It's not obvious to me that this isn't going to work, but yeah, it's just not going to work. And there's just more. I'm just going to give you like 5 examples. The integral of root x cosine x dx. Again, not possible. The integral from 0 to 1 of root 1 minus x cubed. No antiderivative. The integral from 0 to 1 of e to the x squared dx. No antiderivative. All right, all of these functions, so what we say about these functions is they do not have antiderivatives, which are so-called elementary functions. So these functions do not have so-called elementary antiderivatives, which is another way of saying, okay, this is a little bit of a subtle point I'm going to make right now. It's not that they don't have antiderivatives. Every function has an antiderivative. It's that they don't have antiderivatives which are anything you've ever recognized before. Okay, so what is an elementary function? Loosely speaking, an elementary function is any function which is like a bunch of x's and constants and adding and taking cube roots and trig functions and logarithms and crap like that. So take any combination of sums and products and compositions of anything you've ever, I mean, take the most disgusting thing you can possibly think of, you know, like the cube root of 7 minus ln of the, you know, arc sine of the 4th root of x plus 5, you know, over, you know, cosine of, what else is left? 3 to the x, you know, whatever. That is still an elementary function because it's just a composition of functions that we know about already. These guys do not have elementary function antiderivatives. And sometimes this is phrased as there is no closed form expression for their antiderivatives. That's kind of what elementary means. No closed form expression for their antiderivatives. All right, now I'm just going to dwell on this again for a second because they do have antiderivatives. For example, let's take this one over here in the bottom left-hand corner. What is, suppose I say that the derivative of big F is root 1 minus x cubed. And I want to know what F is. This is basically me, this could be rephrased as me saying, what's the antiderivative of root 1 minus x cubed? Anyone have an answer? Even though I just told you a second ago that you can't do it, there actually is an answer. It's kind of like a wise-ass answer.
What if?
But it is the perfectly correct answer.
Does not
F
exist.
prime of x.
All right, the answer to this, the answer to the function whose derivative is root 1 minus x cubed
1 minus x cubed?
is the integral from 0 to x of root 1 minus t cubed dt. Do you agree that by the fundamental theorem of calculus, then the derivative of this function is that?
Yes.
All right, so this is weird. This is kind of a weird conversation we're having right now because I'm sort of on the one hand I'm sort of saying that they have no antiderivatives, but they do have antiderivatives. This is a perfectly legitimate function. I mean, it is a real function. And if I wanted to know what this function was, I could I could try to compute it. But this is not elementary. So this is not a so-called elementary function. And it certainly doesn't help me do the integral because the whole point of the FTC is I need to know an antiderivative. Okay, so how do we do this? I mean, so what we're kind of stuck. This is actually sort of depressing and yet exciting at the same time. So suppose I actually want to know what this integral is, I need to know it. This is a number after all. I mean, don't forget about that. This is going to be a number. What is this number? How do we do it?
Draw it.
We could draw it. Then we could kind of draw boxes and just count and hope for the best. Yeah, you could use a crayon and then just weigh your crayon and then just start coloring it in and then weigh your crayon when you're done and see how much crayon you used. Okay, this is actually not, I mean that is an answer, right? I mean we could do that. Right?
Why is he using the word crayon instead of crayon?
It's a pronunciation. It's not.
Crayon, New Jersey. Is that why you guys are laughing? Because I'm saying crayon? That's what we say in New Jersey. Crayon. You guys say crayon? Sounds like you're from Alabama.
It's how it's spelled! It's spelled crayon!
Okay, Mr. Rose,
What?
you said everyone in New Jersey is always wanting to get out of New Jersey, but they did a study, and Maryland is really high. And I
That's
don't know where
because
New Jersey is,
Maryland-
but I think Maryland's higher.
Maryland is
So you're saying
third
people in
because
Maryland are more
is-
miserable than
Yes, it's 49% or something. 49%
want to
of
leave
people-
Maryland?
Yeah.
Yeah.
Because Maryland is a terrible, terrible place. Terrible.
All right. So, yeah, I guess the difference is in New Jersey, there's an obvious superior alternative, which is just hovering over the entire state with a giant dark shadow of coolness that's not you, which is New York City. You guys don't really have that. You could go anywhere. All right. Anyway, back to math. The answer to the question, no one answered, because you started giggling because I say the word crayon correctly, is you just use a calculator, basically. Eric, that's what you do. You just use a calculator. So let's all remember how to do this. How do we do this? Can you just keep hitting TV? Can you just keep hitting volume every time it does that? So that the menu thing. All right, what do we do? Who remembers what to do? Man.
What is it doing?
It just
Hit
does that,
exit.
it just does that sometimes. Hold on, let me just try something.
Just hit exit.
No, but it doesn't really,
Press volume down.
you have to like,
You just press volume down. That would also work.
yeah, but it's, hold on. Ruining my video. Turn off. No. Maybe that'll do. Okay, let's see if that had any effect. All right, what do we do? Hey guys, let's move this along. What do we do?
Math.
Yeah, math 9. It's actually nicer if you just put it in. It's nicer if you just put it in y1 first. It just ends up just being easier. So you have fewer parentheses. So this is the square root of 1 minus x cubed. Everyone cool with this?
Yeah.
Now quit out, and now you just go math 9, and we want to integrate vars y1. We want to integrate this function from with respect to x from 0 to 1. And the answer is, takes a little while, but our calculator is just going to crank it out, and the answer is 0.84, blah blah blah. All right, so what is the point of this? The point is, this is a perfectly intelligible, reasonable question to ask. It is a number. It does have an answer. And the only thing we know how to do at this moment is to ask our calculator. So, what's the obvious question, Eric Chen, this being the magnet program and like blah, blah, blah?
What?
How do we do it?
What?
How do we do it ourselves?
Yeah, how does the calculator do this? Right? This is the question this is the question we need to answer for the next basically 2 hours of this class is how does the calculator figure that this is 0.841? Alright, so what do? What's one way? One way you know how to do already. Let's take a new example. So we're going to deal with this example for the next long time. So let's take the particular integral. Let's take the integral from 0 to 2 of e to the x squared dx. Okay, first let's cheat. No, don't turn the TV off. Can you turn it back on? First let's cheat, and can everyone just do this really quick and figure out what that number is? Wait, is someone doing it on the calculator?
Oh.
Yeah, Sammy. Or
I can do it.
Rob Rose. But like fast, like extremely efficiently and quickly, and then get it done.
Okay.
Okay, he's being too slow. What's the answer?
No, I got it. I can do
Did you
it.
get 16.4526, blah, blah, blah. I'll even go a couple more decimal places. All right, how, and you have to be careful, you got to be careful with your parentheses. Robert, go back to y1. You got to be careful with your parentheses. It's e to the, parentheses are needed there. All right, can you guys nod gently if you got this number? Okay, good. All right, so the big, massive question that we need to be answering for the rest of today and all of next class is, how does your calculator do this? All right, what's one option?
16.45.
What's one option?
3.
What's one option? Guys,
Three
you
volumes.
know. Yeah, just specifically, what are some of our methods? Think back to before you knew the FTC. How would you have done this? Let's use the right-hand rule. Alexander says, dude, let's just go back to RAM. How do we do RAM? Well, we draw a picture. So let's draw a picture. All right, first of all, I need to make a graph. Let's make a graph. If you take, 2 squared, that's 4. E to the 4th is, e squared is about 7, so e to the 4th is probably about 49. Can somebody just, going to be, Robert Rose, I'm sorry, but I just don't trust you. I need someone who's extremely attentive to, as I'm saying something, they're already 3 steps ahead of me.
Oh, I'm making
Yeah,
a
good.
graph.
Good, beautiful graph.
Yeah.
Can you hit the volume button?
Volume? Oh,
Yeah,
there's no
it's a
volume.
2-part job. Juniors, stay on the ball.
Okay, we can do this.
Yeah, good.
We can
All
do
right.
this.
So, can you go back to the home screen? That is the graph. It's a beautiful graph. I love it. I love you.
Okay.
Can you tell me what e to the 4th is?
E to the 4th. E to the 4th.
Oh yeah, that's 55 basically. Okay, so I'm going to make a graph, not exactly to scale, but basically when I plug in 2 I get roughly 55, when I plug in 0 I get 1, and so basically the function I'm looking at looks something like this. Do you agree? Yeah, good. Now how do we do RM? How does RM? Oh, let's pick a particular thing. Let's use n equals 20. You know what I mean by that? use 20 rectangles. So if we're using 20 rectangles, then what is the width of each rectangle?
1/10.
It is 1/10, because delta x would be, 2 minus 0 over 20. That is 1/10. So delta x is 1/10. So let's start drawing some rectangles. So here, I'll draw a rectangle. Zoom, zoom, zoom. Chicka, chicka, chicka. And then I like to do dot, 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 and then just head for the last rectangle. So this just helps you think about the process. Okay, and then what are these x coordinates? Like what's that x coordinate right there?
0.1.
Yeah, that's just 0.1, and then that's just like 0.2, 0.3, and eventually we're gonna get to the, or maybe I should write this in a pattern kind of way, right? That's 1/10, that's 2 times 1/10, that's like 3 times 1/10. And how many, and we said there are
20 times 1.
20 rectangles, right? So this last rectangle is gonna be 20 times 1/10. Everybody with me? And that is in fact 2, so everything's looking good, our logic makes sense, I'm happy. I'm actually really, really happy. Alright, so can somebody please volunteer to express the sums of the areas of all these rectangles using sigma notation? Sigma. Ercan, do it.
I equals 1.
It's not n anymore. How many rectangles do we have?
Yeah.
20.
F of x. F of delta x I plus. Wait.
F of delta x I.
He's fading.
Yeah.
It's f of,
Delta x.
yeah, it's just I times 1/10, right?
Oh.
In this case, because we're starting at 0, so it's easier this time. And then what's the width of each rectangle? 1/10, so we can actually just put that on the outside. Am I going too fast, or is that pretty much okay? Candy, cool? Okay, now let's do it on our calculator. Do you remember how to do this?
No.
We did this like one day. Oh, by the way, we have a name for this number. Okay, first we'll do it. So you do this whole sum sequence thing. You want to take over for a minute? This is definitely a day to like have your calculator. If you don't have your calculator, it's kind of really bad. Look on to the person next to you or something. But you do this whole sum sequence thing. First of all, it is really, really useful to put the function in y1. And you can just refer to y1. You don't have to refer to the function anymore. All right, so then you construct the sequence. Remember, you go to list, second list, operations, and you construct a sequence. And each term of the sequence should be in the form y1 of, what does the general term look like? X over 10, right? Vars, y vars, function, x over 10. In other words, I want to plug in, I want to basically take e to the x over 10 squared. You guys with me? You cool? It's not so hard, right? Comma x, comma, and what do I start with?
0.
So I start with 1, right? I start with 1 and I end with
20.
20. And what does that do? That produces a sequence of length 20, and all of these numbers represent the heights of each of the 20 rectangles. Everybody with me? And then I want to add them all up. Josemine's coming back to you. We did this like one day really quick. So actually, if you want to be cool, you can do it all in one big line, because it's going to be 1/10 on the outside of the sigma, and times the sum, which is under list, math, sum. And you want to take the sum of the sequence determined by var. I could just do answer, but I'm just doing it all over again to just kind of show you that you can just do it all in one big line. y1 of x over 10, close the y1, comma x, comma 1, comma 20.
Where do we find sum again?
Close the sequence, close the sum.
Where do we find sum?
Sum is under, man, you really like to use calculator.
Second.
Well, you took that calculator.
Oh, yeah,
Second best
that's
math.
true, but.
That's
Okay, and if I hit enter, oops, if I hit enter, it's gonna take a little while and it's gonna give me 19.313. Can you guys nod gently if that is the answer you got also? Right, we have a name for this, we call it R20. So R20 just represents the area as approximated with 20 rectangles using RRAM. And what we got for R20 is that it is 19.3139. And if you want to, you can actually store that in your calculator as R or something like that if we need to reference it later. All right, are we generally okay with the syntax? You're just gonna get better at it. I mean, you guys are like, take comp sci stuff, so it's like not that hard. All right, some comments. Does anyone have a comment? Looks like a lot of interesting comments to make right now.
What if we're not too loud?
Everyone start talking at once. Daniel, what'd you say?
Are we allowed to use a testing? Are we allowed to use a testing?
Yeah, for this process, you have to use, we're definitely using a calculator, right? Yeah, this is a lecture which exists in the 20th century or 21st century. So this is assuming that you have technology which will compute things for you. We're talking about how to use that technology. So wait, there's some interesting thoughts. Robert, stay focused, please.
What?
Some interesting thoughts. How about like, is this a good answer or not? That's like an interesting
No, that's
thought.
not that accurate.
Yeah, specifically because we cheated,
And
we know how not accurate it is.
We only explain how we do it.
Okay, right, it's off by like a lot. That's what I was hoping you guys would say. Just qualitatively, using just your own feelings and opinions. Do you agree that this is like quite dramatically off? We're off by like 3, which is like a lot. Whereas this is like a 15% error or something like that. Yes. Of course, this is circular because I don't know that this is the true answer. Is that what you're gonna say?
No, but also we just haven't taken the limit yet, so.
Oh, he's saying that it has to do with the fact that we're using only 20 rectangles. But there's another reason, again, we're speaking sort of informally here, there's another reason why, say some more things.
Oh.
There's like 5 things to say, yeah,
Are
your
we
hope.
overestimating?
Yes, look at the picture, right? This is clearly going to be an overestimate. So, first of all, if I had not cheated and used Math 9, I could tell you one thing for sure, which is that the true integral has to be less than 19.3139. Why do I know this is an overestimate, besides just duh, I looked at it?
Because when you use RRAM and the function is increasing, then
Correct.
there's an
Okay, so that is a key thought, which we discussed this like previously, right? But that is just like a theorem, which I'm not going to prove formally, but it is a theorem you could prove formally. If you have an increasing function and you use RRAM, then what you get is an overestimate. So observation number 1, this is an overestimate. Observation number 2, is just off by kind of a lot. Observation number 3, it's off by kind of a lot, if in some ways if you think about it, because, can you go back to the graph, Rob Rose?
Yeah.
If you go back to the graph, you can see that because this function gets so big, so fast, it's like this last rectangle, if you kind of think about it, could you actually take us, yeah, beautiful. Can you put us on the interval from 0 to 2 though, please?
0 to 2. When
Yeah.
you go 0 to 2.
Perfect, hit it. Yeah, if you look at what's happening is that the function gets so big, so fast right at the end, is that 20th rectangle is actually going to have tons of area which is not under the curve. Are you with me? Okay, so that's something to keep in mind. All right, so intuitively this is going to be way, way off. This is definitely an overestimate. RRAM overestimates increasing functions. Oh, by the way, have we actually proven that this function's increasing or just looks increasing? Should we just like do that really fast just so we can, no? Yeah, that was a fake suggestion. We are gonna do it. If the derivative is e to the x squared, if the function is e to the x squared, then the derivative is,
We know that e to the x is increasing.
what? The derivative of e to the something is? E to the something back inside derivative of the something. So this is just 2x e to the x squared. And say something intelligent about this derivative on the interval 0, 2. It's positive, right? F prime of x is positive on the interval 0, 2. It's positive because it's the product of 2 things which are each positive on the interval. So actually I'm not just looking at the graph, I've demonstrated using calculus that this function is positive, or that the derivative is positive, so that the function is increasing, so that this will definitely be an overestimate. Okay, what is an intuitive thing to do next?
Also, if it was decreasing, it would LRAM.
Yes, now let's use LRAM. Because, Josephine, why is that a good idea?
Because we just got an overestimate, so now we should get an underestimate.
Yes, intuitively speaking, if we draw this picture, I keep saying that. If I draw this picture again, this is like 55, and the function looks kind of like this. Now, if I use LRAM, this should be an underestimate for two reasons. The picture, and other reason is that that is just a theorem that if your function is increasing, then LRAM is an underestimate.
Why don't we just like average the two?
That's an idea. First, let's get LRAM. So let's do it the same way. Let's do it n equals 20. And now a little bit faster because we're getting smarter and smarter every second. Let's figure out what are the heights of these rectangles. Well, this is still, delta x is still 1/10. That's still like 1/10. That's still 2 times 1/10. Still 3 times 1/10, etc. But now, what's going on? Someone give me the sigma. Give me the area of all of these rectangles using sigma notation. Should I call someone new? Luis Paz. You can do it, man.
Okay, so from I equals 1 to 20.
Sigma.
Yeah. F of, wait, there's a zero, so.
You can do it, man. If it's wrong, it's okay too. We'll just fix it. Don't be scared. Should we write out a couple of them? What's the first one? What's the area of the first rectangle?
So 1/10 times,
No, it's not f of 1/10. Because the height of the first rectangle is determined by the value of the left endpoint. So it's f of 0 times, okay, now we're going too slow, times 1/10. And what's the area of the second rectangle? F of 1/10 times 1/10, etc. And then what's the area of the last rectangle going to be?
F of 19/10.
F of 19/10, comma 1/10. Okay, so how can I do this?
I minus 1.
Someone have an idea? Okay, you can do all that I minus 1 crap, but now if it makes it easier for you, you can just start your sigma. You don't have to start your sigma at 1 because we're just going to be typing it into the calculator anyway. So I think it's actually easier if you just start at 0 and then you stop at 19. And then what's the rule? I think it's just f. It's still just f of x over 10. There's no secret way to do this. You just have to kind of like mess around and do a little like guess and check and just like figure it out. Actually, are you with me? So yeah, I over 10. Sure. It's going to be x on my calculator, but yeah. So the first rectangle should have height f of 0. The 0th rectangle rather should have height f of 0. The 1th rectangle should have height f of 1, and it just works out.